Okay, we're looking at the 9C practice test in our video today. The first question says, in a study of the effects of acid rain, a random sample of 100 trees from a particular forest is examined. 40% of these show some signs of damage. Which of the following statements is correct? Because our sample is 100 trees and we know that 40% of them show damage, the 40% is a statistic because a statistic is defined to come from a sample, while parameters come from population values. So the answer is B for number 1. For question 2, refer to the previous problem. Which of the following statements is correct? The sampling distribution of the proportion of damaged trees is approximately normal. That is the answer because the central limit theorem says that for any sample that's at least 30 in size, the sampling distribution will be approximately normal. Doesn't matter what shape the parent population is, as long as the sample is over 30, the sampling distribution will be approximately normal. Question 3, which of the following statements is or are true? Statement 1, the sampling distribution of x bar has a standard deviation sigma over the square root of n, even if the population is not normally distributed. That's the definition of the standard deviation for a sampling distribution, so I know that statement is true. Statement 2, the sampling distribution of x bar is normal if the population has a normal distribution. That's definitely true. Anytime the parent population is normal, any sampling distribution will also be normal. And statement 3 says when n is large, the sampling distribution of x bar is approximately normal, even if the population is not normally distributed. And that's basically, the statement 3 is basically what we dealt with in question 2. So all 3 of these statements are true, and the answer is D. Question 4, suppose we're planning on taking an SRS from a population. If we double the sample size, then sigma, standard deviation of x bar, will be multiplied by what? So I'm starting off with my formula for standard deviation of x bar, which is standard deviation over the square root of n. But I'm doubling the sample size, so I'm doing 2n. So essentially 2n, you can break up this root into the square root of 2 times the square root of n. So if I double the sample size, essentially I'm multiplying by 1 in the numerator over the square root of 2. So my answer is choice B. You got to be careful with this one to not just pick A because you have square root of 2 down here. Remember, it's in the denominator, so it's 1 over this value. Question 5. If a statistic is used to estimate a parameter is such that the mean of its sampling distribution is different from the true value of the parameter being estimated, the statistic is said to be B-biased. Question 6. A machine is designed to fill 16-ounce bottles of shampoo. When the machine is working properly, the mean amount poured into the bottles is 16.05 ounces, with a standard deviation of 0.1 ounce. If 4 bottles are randomly selected each hour and the number of ounces in each bottle is measured, then 95% of the observations should occur in which interval? There's a couple key parts to this question. The first one being the fact that you're taking a sample of 4. So the standard deviation that they give you of 0.1 is going to end up being adjusted by using the formula for the standard deviation of a sample, which is standard deviation over the square root of n. So we're plugging in our values, n being 4, the square root of 4 is 2, 0.1 over 2 is 0.05. So that's the standard deviation we're going to be working with for the problem. The second key to understanding this question is they ask you about 95% of the observations. And you're going to have to think back to chapter 2 on this for the 68, 95, 99, 7 rule, which says that 95%, because that's the middle number, 95% of your data falls within 2 standard deviations of the mean. 68% falls within 1 standard deviation, and 99.7% of the data falls within 3 standard deviations. So the fact that they tell me 95% means I have to look at 2 standard deviations away from my mean. So my mean is 16.05. And I'm going to go plus or minus 2 standard deviations, 2 of the 0.05s. So plus or minus basically means either direction. So if I add, basically, so 2 times 0.05 is just, it takes me back to the original value, 0.1. So 16.05 plus 0.1 is 16.15, and 16.05 minus 0.1 is 15.95. So your answer is C on question 6. For question 7, it says Dr. Stats plans to toss a fair coin 10,000 times in the hope that it will lead him to a deeper understanding of the laws of probability. Which of the following statements is true? A. It is unlikely that Dr. Stats will get more than 5,000 heads. 5,000 heads, if he did this trial a whole bunch of times, like that's the expected value, but there's no reason why he couldn't get more than that or less than that. And he's probably, there's no reason why he couldn't get more, so it's not A. B, whenever Dr. Stats gets a string of 15 tails in a row, it becomes more likely that the next toss will be a head. That's not how probability works at all. It's not like the coin changes its probability. Every time you flip a coin, it's still 50-50, whether you get heads or tails. It doesn't really matter what happened in the past. The next toss is not affected by the past. Part C, question choice C, the fraction of tosses resulting in heads should be close to a half. That's the concept here of probability. If you have a 50-50 chance, you would expect to get about half of them heads. You're not always going to. You might not, but that's the expectation. So the answer here is C. Just briefly talking about choice D, the chance that the 100th toss will be a heads depends somewhat on the results of the first 99 tosses. That goes back to why B is not correct, because the 100th toss does not at all affected by anything that happened in the past on the first 99 tosses. And then I just threw in choice F as a joke. Dr. Stats is insane. Anyone who's going to go out and flip a coin 10,000 times obviously has too much free time on their hands. Question 8 says, the following window shows the results of a computer simulation that is designed to illustrate sampling distributions. And the question says that we need to briefly discuss the bias and variability of the sampling distribution of the sample median. And so when I looked at this question at first, and probably when you look at it, you are like, what on earth is going on here? What do all these graphs mean? And you have no idea how to interpret them or discuss the bias or variability or find any bias or variability just in these pictures. So you have to look at them pretty closely and make sure you read. And I know that the wording is pretty small, but here we have the parent population, and you can see that it's centered over this number. And what is that number? Well, it's not this, it looks like 1 right here, but it's not 1. It's the data is given over here. The median value is 16. So the parent population has a median of 16. And when we look at sample data over here, sample here, we see the distribution of the medians. When our sample size is 2, you can see this distribution, and it's fairly spread out, but it's centered over the value of 14. But when we increase our sample size to 25, you can see n is 25 here. Obviously, the data is not nearly as spread out, and it's a lot closer to this central value. What is the central value? Well, the central value, the median, is 16. And so the concept of what you should see from that is that as your sample size increases from 2 to 25, that your data is less variable because it's not as spread out, and you're having more values that are closer to the population median value of 16. You can see that when we increase the sample size, first the median was 14 when we only had 2 in our sample, and now it's 16 when we increase the sample size, and 16 matches the median value of the population. So the way I discussed that is I just said the population median is 16, and when a sample of 2 items is taken, the median is 14, but if a sample of 25 is taken, the median is 16. Thus, as the sample size increases, the data more closely resembles the parent population, so there's less bias as you increase your sample size. which another way of saying that is that the variability decreases as the sample size increases. The variability just meaning the amount, how far spread out your data is. You can see obviously the data is a lot more spread out here than it is here. So as you increase your sample size, your variability goes down. Question 9. It says, in a test for ESP, extrasensory perception, the experimenter looks at cards that are hidden from the subject. Each card contains either a star, a circle, a wave, or a square. There's 4 options there. As the experimenter looks at each of 20 cards in turn, the subject names the shape on the card. Part A, describe the design of a simulation to estimate the proportion of correct guesses assuming the subject does not have ESP using the partial random digit table below, and then perform the simulation. So to design my simulation, I need to figure out what's the proportion, what's the probability that this person is guessing the question, guessing the card correctly. And if there's 4 options for each card, there's only 1 card that's correct for each of those 4 possibilities. So the probability of a correct guess is 0.25, which is 1 out of 4. So because I have a 2-digit probability here, I'm going to have my table values count off by 2 digits. So I'm letting 00 through 24 represent a correct guess, and that's 25% of all my 2-digit numbers. And 25 through 99 represent an incorrect guess. I'm going to count off by 2 digits, so I'm counting every second number so I can get these 2-digit numbers. And I'm going to repeat counting off by 2 digits until I have 20 numbers, until I've obtained 20 numbers. So I need 20 numbers because we're looking at 20 cards. So first off, 35, then I counted off, so I put up a space, then 47, put a space, etc., etc. So I did this until I had 20 numbers. So 35, 47, 65, 59, etc., 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 all the way down until my 20th number was down here, 24. So what I did is I underlined any number that represented a correct guess from 00 through 24. I got the number 16, the number 04, 07, 20, and 24. I wrote them here. That was 5 times that I got a correct guess. 5 out of 20 is 0.25. So this 0.25 is my p-hat. It's my sample probability based on this sample right here. Then it says, when the ESP study described above discovers a subject whose performance appears to be better than guessing, meaning they might actually have ESP, the study continues at greater length. The experimenter looks at many cards bearing one of 5 shapes, so now they're lowering the probability of you getting the right answer by increasing the amount of choices you have. Star, square, circle, wave, and cross in an order determined by random numbers. The subject cannot see the experimenter as he looks at each card in turn in order to avoid any possible nonverbal cues. The answers of a subject who does not have ESP should be independent observations, each with probability 1 out of 5 of success. We record 1,000 attempts. So part B of this question, what are the mean and standard deviation of the proportion of successes among the 1,000 attempts? So because they italicize the word proportion here, the key is you need to be taking the mean of p-hat. And looking back at your formulas from this chapter, the mean of p-hat is defined to be p, the parent population proportion, which was 0.2, which is what you get when you do 1 divided by 5. For the standard deviation of p-hat, the formula is the square root of pq over n. If p is 0.2, q is 0.8. So 0.2 times 0.8 divided by n, which is 1,000. Do that, and then take the square root of it, and you will get 0.0126. Part C, find the probability that a subject without ESP will be successful in at least 24% of the attempts, the 1,000 attempts. Show your work. In order to do this, you need to check that you can use normal commands. So you need to check that NP and NQ are at least greater than 10. So I did that. I got 200 and 800, which are obviously both over 10. So I said because of that, therefore, the 3 dots, therefore the sample distribution is approximately normal. So I was able to use my normal CDF command. At least 24% means my lower bound is 0.24, my upper bound is essentially infinity, so I use 10,000. Lower bound, upper bound, mean, standard deviation obtained from part B. Plug that in the calculator and you get 7.503 blah 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 e negative 4, which means shift your decimal space 4 places left.